Hello all. We will be starting a simple exercise which we are going to solve it in abacus. So let's consider a simple problem. So you are going to have, let's say, you are going to have a bar. We will be considering a very simple problem. So the bar is made by using steel and you are going to apply a load of 10 kilonewton. So then the length of the bar, let's say we are going to take it as 4.5 meter. Length of the bar is 4.5 meter. And the area of cross section, we can assume that, let's say 50 millimeters square. So then the Young's modulus, it is 200 gigapascal. Then the Poisson ratio, let's say we are assuming it is 0.3. So this is a problem within our hand. So 50 millimeter, we will just convert it into SI unit, 50 into 10 raised to minus 6 meter square. Then 200 gigapascal, 200 into 10 raised to 9 Pascal. Then Poisson ratio is 0.3. Then the load, let's say we are going to apply a load of 4.10 kilonewton. So it is 10,000. So this is the problem in your hand. So basically the stress is equal to force divided by area. That is equal to, in this case, it will be equal to 200 megapascal. Then strain will be equal to stress divided by Young's modulus. So if you substitute, you are going to get 0.001. And the total deformation of the beam, let's say it's delta L, that is equal to the strain into the length. If you 0.001 multiplied by 4.5 meter, so you are going to get the deformation 0.0045 meter. Then the reaction force from the support. So let's say we will be having a reaction force that, if you take its reaction force, is we denote it as F1. So then the reaction force we are going to get, this will be equal to minus 10 kilonewton, minus 10,000 Newton. So this is the problem in your hand. Now we will be solving this same problem in abacus, which will give you an overview of how we are able to model the problems in abacus. So let's look at that one. So just opening the abacus window. So once you have opened the abacus window, the new model base you can take it. So whatever we are going to use it with standard explicit model, electromagnetic model, we are not going to discuss. So this is what we need to do. We will be selecting a new model database with the standard explicit model. So this is the window in front of you. Now you can see here you can see here it is module, and the module you can see you are having part, property, assembly step. So these are the different steps which we are going to follow it. So this is, we can call it as a module. For each module, you will be having the option here on the left side. So you will be having multiple ways to take that option. But currently we are going to use it, the option which is available here. So the similar option probably will be available here. We can solve it from here also. So we will be using here. That is what we are going to use it. Now what we need, actually, we are going to have a bar or steel bar. So then we will be modeling it in 1D element. So the geometry in our hand will be having only a line which have a length of 4.5 meters. So we are actually making a one-dimensional modeling. So initially you have to create the geometry. That's the first thing which we are going to do in Abacus. So when you look at, we want to create a geometry. The geometry is basically a line which is having a length of 4.5 meter. That is the only geometry which we are going to create because we are analyzing this problem by using a one-dimensional element. So the geometry will be only a single line of 4.5 meter length. So in order to create that one, you will be having an option here that is called create part. So once you click on this create part, so you will be having this option. You have a 3D modeling, then you have a 2D planner, and you are going to have axisymmetry. So currently our modeling is one dimension. So one dimension is coming inside the 2D planner. So this is the first thing we need to take it. The modeling our space will be equal to 2D planner. Then after that, it is going to ask the different other option. What is the body which we are going to look at? The body which we are going to look at is a deformable body. We are not looking at the rigid bodies. The other two options, you can call it as a rigid bodies, which we'll be using in other different scenario. So currently we will be concentrating on deformable body. And after that, you can see it is shell. Shell, if you want to create a, since we are dealing with 2D, if you want to create a plate, you can use shell element. And but here we need only a single line, which is having 4.5 meter length. So we can select wire. Point is the other option. We are having only one point. So then you can see the approximate size. Approximate size, which is going to give you, because if you look at a graph sheet, you have first quadrant, second quadrant, third quadrant, and fourth quadrant. So approximate size, when you specify whatever the magnitude which you are going to specify here, which is the length of the first quadrant. So the length of the size of first, second, and third and fourth quadrant will be remain same. So which is basically going to ask, sorry, probably it is going to ask the total size of the graph sheet for both first and second, length of first and second quadrant. So let's say what we are going to have here. I want to create a line of 4.5 length, 4.5 meter length. So if I want to bring it inside the graph sheet, so let's say I'm just going to create, let's say 10. Okay, so I will be getting a graph sheet which having 10 meter length and 10 meter width. So when you look at one quadrant will be 5 into 5. That is what we are going to create. But this doesn't have any importance. I'm just making it as approximate size is equal to 10. So we will be continuing this one. Now you can see here, this is the graph where you are able to plot it. But if you are plotting it outside this one, that is also fine. So now what we need to create a line which is having a length of 4.5 meter. And it has to be horizontal. The line is horizontal. So when you look at here, you are going to have an option, create lines option. So where we are able to create a line. So if I click here, I am able to create a line. So once I am clicking here, you can see at the bottom, Abacus is asking a starting point, and then after that, it is going to ask an ending point. So let's say we are going to draw a line where one point of the line is on the origin and the second point is 4.5 meter away from the origin along the x-axis. So the first point of the line is 0, 0, that is the origin. So you can see one line is going to be created where one point of that line is origin. Now we need to define the second line, second point. Second point also I can enter on the same point. It is 4.5, x coordinate is 4.5, then y coordinate is 0. So you can see Abacus has created a line of length 4.5 meter. So remember that which doesn't have an inbuilt unit. I am assuming all the values which I am going to enter in SI unit. So the length is also I am going to enter in SI unit. So now I got a line of 4.5 meter length. Then after that, I don't need the second line. So I will just escape it. So you will have, when you click on the right click on the mouse, you will have cancel procedure. You will just cancel the second segment of the line. So now the geometry is completed. When you complete the geometry, then here at the bottom, you will see sketch the section for the wire. We have done that job. So if you have done the job, then I can click done. So my geometry is completed. Now what we need to go? I need to go for the property. So property, what we are going to specify? We are going to specify the material properties. And we will assign the material properties to this geometry. So you can, after the part, you can move property. So on the property, let's look at only on the right side this menu. So here you can call it as a material manager. If you click on the material manager, it is going to give an option to create a material. So you are having an option for creating the material. Just click on this create material. Then you can see the default name Abacus is giving is material 1. You can change that name. Let's say I have changed it to steel. So it need not be required, but just I'm just using the facility only. So after that, if you go down on the general, you will see different properties you can enter density. These are the other properties. Then on the mechanical, you can see elasticity, plasticity, damage of ductile material. You can see free viscoelasticity, different types of things you can see here. So what we have interested here, the steel is going to be, we have an elastic limit, this linearly elastic behavior. So whenever you are going to have linearly elastic and isotropic material, we can select this elasticity. We are not going to do plasticity now. So on the elasticity, you are having different types of elastic, hyperelastic, hyperform. These are all different other properties. What we are interested in is purely elastic, linear elastic. Click on this linear elastic. When you click on that linear elastic, you will be having an option for isotropic, orthotropic, anisotropic, different types of options are available. So right now our steel is isotropic material. That is what we are assuming as steel as isotropic. And after that, you can see some use temperature dependent data. We are not interested in temperature dependent now. We are handling everything is at room temperature. So there are a number of field variables, just ignore it for now. So whenever the material is linearly elastic and isotropic, in order to define that material elastic properties, you need two properties. One is Young's modulus and second one is Poisson ratio. So these properties you can enter here. So Young's modulus, it is 200 gigapascal. So I'm just entering 200 into, I'm just using 10 raised to 9. Instead of that one, I can use E raised to 9. So 200 into E9, it indicates that 200 into 10 raised to 9. Then the Poisson ratio, it is 0.3. So all the material properties I have defined for the current problem. So click OK. So I define a material of steel. Now I have defined a material of steel. Then I have a geometry which is in the screen. Now I have to tell the software that this geometry belongs to this material is belong to this geometry, or this geometry has to be the material has to be assigned to this geometry. So before that one, I have to tell whether it is solid, homogeneous, such things also I have to define it. So you will be having an option here, create section. You will be getting the similar option here, section manager. You will be having an option for create section. On the create section, you can see solid, homogeneous. Then you can have shell homogeneous. You can have beam. Right now, our geometry is one dimension. So either I have to select beam or truss. So we will be selecting truss now because that is what we are discussing now. So truss. Then we will be continuing this thing. So then it is asking to define the material. So right now I am having only one material. Right now I am going to have only one material. Right now I am going to have only. So here you can see the material you can drop from, you will get from drop down menu. Right now I have only one material, that is steel only. So you can select, that is the default one now. Then below that one, you can see it is asking the cross section area. So cross section area in our hand, it is 50 millimeters square. That means 50 into 10 raised to minus 6 meters square. So I will be entering 50 e raised to minus 6. So click OK. So I have now I define a section where the element is plus and the area of cross section is also defined. Now I have to tell that this section, this cross section is defined for this geometry. For that one, we are going to have an option section assignment manager. So click here. Then you can create. So you just select this geometry now. Then click done. So we have created only one section, that is a steel section with a truss element. That's the only section I created. If you create multiple section, you will be having a drop down menu here. Now you don't have a drop down menu. The default one is section 1, which is actually steel, material is steel, and the section is truss, and the area cross section is 50 millimeters square. So that is the default one, and that's the only one. Click OK. So now the section is assigned here. And after that, all the properties which I have defined in the property module. Then after that, you are going to have an assembly module. Assembly module, why are we going to use it assembly module? Assembly module which we are going to use it for whenever you are going to have multiple number of parts. But even if you are having a single part in your analysis, still you have to bring it in the assembly window. So that is what we are going to do here. Create instance, you can just create instance. Then you are going to have only one part. You don't have, if you have multiple part, everything will be appearing here. But now, right now, we are having only one part. So part one, then you can see dependent or independent. So that actually we will be discussing later. So dependent, I'm just selecting the dependent mesh on part. Remember that we can do mesh on part only. Okay. So that we'll be discussing when we are discussing the meshing. So click OK. Now assembly is completed. After the assembly is completed, you are going to have step. So in the steps, you are going to tell the software that what is the type of analysis which we are going to do it. So in that one, you will be creating the step here. You can just use the create button. And then you are going to have initial step one. You can, if you want to give some name, you can give it like a analysis of a bar under axial load, something you can name it here if you want. Otherwise, we will keep it as step one itself. Then you can see here you will be seeing different types of analysis it can do: coupled temperature displacement, coupled thermal electric, dynamic implicit, dynamic explicit. So what we are analyzing now, it's a linear static analysis. So we can select static general analysis. So click continue. So I'm just going to click continue. And after that, you can see the time period. Time period is important for whenever you are going to discuss about the transient problem where time is coming into picture. But this is a typical solid mechanics problem where time period is not coming into picture. Whenever you are having such a problem, the time period we are going to keep it as 1. It's 1. So it indicates that the load is going to apply within that one second. So if you, that is how it is load is going to be applied. So this is actually showing NL geometry, actually showing nonlinear geometry. We are not discussing anything about nonlinear geometry now. Our analysis purely linear. And next thing you can see incrementation. So fixed we will not select. We will be selecting automatic. In that one, you can see maximum number of increments. So our analysis, whatever we have discussed in the class, we need only one increment to complete it. There is no problem if you give 100. The only thing it is going to take more time. But with our current computation power or with our current computer, even if you select 100 or one, it does not matter actually. So the time difference between one increment and 100 increment is so small that you cannot identify. It may be one is maybe 1 millisecond, then other maybe 10 times of that one. It's according to that one only. Anyway, it is not, you are not able to identify it. So we will be selecting only one. Maximum number of increment is only one. Increment size, it is calling what is the initial increment. The minimum increment also we will keep it 1. Maximum increment also we will be keeping 1. So everything we can keep it 1 because we are actually conducting a linear static analysis. Okay, so click OK. So step is created here. And after that, what you are going to do, step is completed now. Then you are going to have interaction. Interaction we are going to bring into picture whenever the friction or there are interaction between two bodies is going to be involved. Let's say you are having some sliding motion between two bodies, then friction is going to come into picture, or you are going to have convection heat transfer, radiation heat transfer. So all these condition, let's say you are having machining operation, chip is going to pass over this tool. Such things, whenever we are having some interaction or we are analyzing some sliding motion between the two bodies. So interaction is going to come into picture only during that time. In our case, we don't have any interaction. So we can just neglect this interaction. Now we will be going to the next module, that is load module, where I want to define the loading condition as well as the boundary conditions. So on the load condition, you can see here, you are able to create load, or you can click load manager. where you will be having an option to create load. So when you click on load, you can still give any number to the load. You can select which step you want to apply. Right now it is step number 1. Then you can see what we are going to apply. It's a mechanical loading. You can see concentrated load, moment, pressure, shell edge load, body force. If you are defining gravity, line load, gravity is separate. Or other force you can apply as a body for magnetic force or something. So all these ones are available here. What we are applying here now, it's a concentrated force. So we will be just fixing on concentrated load. So click continue. Now it is asking to selecting the point. Which point I have to select? I will be selecting the rightmost point. So I'm just selecting this point. Then I will be clicking OK. Then it is asking the magnitude of the load. So remember that x-axis abacus is denoted as 1, y-axis denoted as 2, and z-axis denoted as 3. Our analysis 1D analysis. So you will be having to enter only 2 components. One is the force component along x-axis and the force component along y-axis. So we are considering a simple bar problem. So you will be having only the load along x-axis. So where we will enter the load CF1. CF1 stands for component of force along first direction. So it is 10,000. 1, 2, 3. So it is 10,000 load. CF2 represents the component of force along y-axis. So it is 0. So either you can enter 0 or you can keep it blank. If you keep it blank, software will take it as 0. So 10,000 along x-axis and 0 along y-axis. Now you can see here an yellow arrow line is appeared, which actually indicates what is the direction of the load. Now the load is acting positive x-axis because you give plus 10,000. And it is going to act on this right motion. So the loading is completed. Now you can see here you are able to create boundary condition. You are having a boundary condition manager here, where also you are going to have an option to create boundary condition. So what we need to apply? We need to apply displacement on the left point. So mechanical, then displacement or rotation, we have to control on the left point. We will be continuing. Abacus is asking me to select the region. We will be selecting this single point. This is the point I have selected. Click OK. So then what we need actually, we are fixing on the left hand. So x-axis displacement will be equal to 0. Y-axis displacement will be equal to 0. And even the rotation about z-axis is also equal to 0. These are the 3 things which is available in 2-dimensional plane. Either that point can move along x-axis, or it can move along y-axis, or it can rotate about z-axis. These are the only 3 possibilities for motion. So everything we are going to fix 0, 0, 0. So that means we completely fix it. So you can see there is a symbol of fixing on the left hand is appearing here. Now we have completed the loading. After that, now we need to mesh it. We need to tell the software that how many elements, the finite element means we need to discretize the geometry into finite number of elements. So what we are going to consider here, we are going to consider the meshing. So we will be selecting mesh. Then when you select the mesh, the first thing we need to do seed, means where we will specify that how many number of division has to be made. And then we will be telling how many elements has to be divided. In 1-dimensional, both are same. Both seeding as well as meshing is same, but it is going to different when you are talking about 2-dimensional. So right now you just forget about that one. So since we select at the assembly point, since we select instead of assembly, we select part. We have to select part. If you did not select part, and if you are going for seed part instance, if you click it, it is going to give an error. Dependent part instance cannot be edited or assigned mesh attribute. So in the assembly, since I have selected part on instance, so I have to select part. So now part 1 is created. And after that, you can do seeding. Seed, what we are going to do, we will tell the software that how many division has to be made on the geometry. The geometry, we have a single line. Now we will ask seed. Then Abacus is asking what is the approximate global size. It is giving a global size of 0.45, which indicates that this line is going to be divided into 10 elements because our total length is 4.5. So if you are having an element of 0.45, you will be having 10 elements. Right now, what we are going to do, we will be dividing into only one element. So I will just select global size is 4.5. So that means that it is going to divide it into only one element. So click OK. So you can see this is the first node and this is the second node which is going to be created. You will be having only two nodes, one node and second node. And the entire geometry is divided into only a single element. So seeding is completed. Then after that, you have to do the meshing. You are going to have an option here, meshing part. Meshing, you have to do it. Then it is asking, okay, to mesh the part. Yes. So remember that in this one-dimensional case, meshing and shading both are almost same. Now, what we need to select the element. So element we will be discussing later. So mesh, you will be having an option for element type. Select this element type. Then software is going to ask, select the region to be assigned element type. So we have the entire region to select. So click done. Then what we need to select the element. You can see the default one Abacus select this beam element, but what we have defined the section is truss element. So we have to select with truss element. You can see standard and explicit. What we are going to do is implicit analysis. So it is standard. We will be discussing later what is implicit and explicit analysis. Then the geometric order is order of shape function, which is also will be discussing later. So these two things we will be selecting and click OK. So meshing is done. Everything is done now. And then after that, what we are going to do? Once the meshing is completed, we will be going for job, where we will be asking the software to solve the problem. So one of the important parameter I missed it to save the file. What you can do that actually you can create a work directory where you are able to solve the problem. So save the file. Sorry, you are able to save the file. So in order to create saving the file, you can just go to save file. Then you have an option set work directory. So work directory you can select. The default one is C and temporary folder. So let's say I'm going to my desktop. So I'm just going to my desktop where I'm going to create a new directory. So let's say I'm going to create applied FEA. So I have created a folder, applied FEA. So where I'm going to create another folder, let's say it is problem number 1. Problem 1. Click OK. So this is the location where I am going to save it. So I just select this problem directory, problem file where everything is going to save it. Click OK. So that everything is going to save there. So whenever we are going to run the software, we will be creating multiple number of files. So Abacus is going to create, not we will be creating, Abacus is going to create multiple number of files. All the files is going to save them. So after that, you can save it. If you want to save it, you can save it. You can go to save option. On the problem number 1, we are going to save it. Save problem number 1. Problem 1. Click OK. So everything we have done. Now we can ask the software to run the job. So click Job Manager. Create. So here you can give some job name where it is going to save. It is going to save the solution where it is going to save it. You can give some name for that file then. So let's say I'm giving maybe PR1, problem number 1, the name of the job, then click continue. These are all things are default. Don't do anything here. Click OK. So now you can submit it. So I will just run the submission. So now you can see Abacus submitted the job. Now after that you will see you can see it is running. So that means the simulation is running now. And once it is completed, it is going to be completed. So you can see the simulation is completed now. So if you want to see the result, you can click here, see the result. So you can see the contour plot. You can see contour plots here. You can just click here. So you can see the default one, Abacus is going to shave the von Mises stress, which whatever it you can see here, it is von Mises stress. And if you want what we are interested with stresses along x-axis. That is what we are interested. But in this condition, it's a purely one-dimensional analysis. So von Mises stress and stress along x-axis will be same here. So you can see the von Mises stress is 2.0 into 10 raised to 8. So you can see here. So the von Mises stress, you can see. Remember that everything which is going to show it in Pascal. So what is the stress? You can see von Mises stress, it is going to see 2.0 into 10 raised to 8 Pascal, which is actually 200 megapascal. That is the result which you can see. So this will be same as if you look at what it is showing in along x-axis also, because there is no stress along y-axis and z-axis. So here, if you want to see the x-axis stress, you can go to here, select yes. Then here you can see S11. So remember that what we are interested in is sigma xx. So if you look at the, just come back here. If you look at the stress tensor, if you look at the stress tensor in a two-dimensional thing, sigma xx, then tau xy, then tau xy, then sigma y. If you are having set, you will be having tau xz. Then here you will be having tau yz. Then tau xz, tau xy, then sigma z. So sigma xx indicates that in abacus, x-axis is 1, so it is going to be 1, 1. So basically, the stress notation in abacus is yes. So basically, this is going to represent S11. So sigma xx is going to represent S11. So in this case, we will be having only sigma 11 and as well as von Mises stress. Y-axis and z-axis stress will be equal to 0. Okay. So just come back here. So this is the stress. We are looking for the stress. Now, this is default one is Mises stress. You can see maximum principal, maximum incline principal, different types of stress. You can see what your interested is sigma xx. So you can select S11. S stands for stress symbol and 11 stands for xx. So it is sigma x. So you can see the stress are same 2 into 10 raised to 8 Pascal. So you can see everywhere the only one color is going to appear. That means stress is constant everywhere. And that value of stress is 2 into 10 raised to 8. Now, what we are getting stress 200 megapascal. Now, what we need strain. So, strain it is represented by E. Strain is represented by E. So, strain also you have principal strain, then sigma, gamma, x, well, different types of strains are there. We are going to have only E11. So, E stands for epsilon in our, E stands for epsilon in the solid mechanics and 11 stands for x-axis strain. So, it's a normal stress along x-axis, epsilon x or E11. So, you can see the strain is 1 point into 10 raised to minus 3. 10 raised to minus 3. So, somewhere you can see if you want to see the, you can see annotation manager. Annotation manager, you can see view annotated option. So, where you are able to convert this one from this type of letter to the digits, you will be having, instead of scientific, you select fix and the decimal place you may increase, say 4, click apply. So you can see the strain, if you look at it, is going to get 0.001. So just compare it with the strain in the theory. It is, the strain is equal to 0.001. Then what we are interested, we are interested in delta L. So delta L is equal to 0.0045. So, but remember that delta S is going to happen on the free end where you have applied the force. So basically you are having, we divide this geometry into one element. So you are going to have first node and here you will be having the second. So what we are interested, the deflection on the second or the deformation displacement of the second. That is what we are interested. So if you want to find out the displacement, here you are going to have an option U. U stands for displacement in abacus and 1 stands for x-axis displacement. U1 stands for x-axis displacement. So just select U here. Right now it is showing the magnitude of the displacement. So that means U1 square plus U2 square, root of U1 square plus U2 square plus U3 square. The magnitude. What we are interested U1. U1 displacement along x-axis. But in this case, displacement along y-axis will be equal to 0 because we are talking about one-dimensional analysis. So U1, what we are interested, U1 means the displacement along x-axis. So you can see here, now you can see here, the red one, it is 0.0045 and the blue one is 0. So which indicate that, remember that always here, the maximum value will be given as red color and the minimum value will be given as the blue color. So in our case, one end is fixed. So minimum displacement will be equal to 0 and the other end is free. And the maximum displacement will be on the free end. So if you want to identify what is the displacement, if you look at the geometry now, the left you can see it is blue color, which indicates around 0. And the right you can see red color, which indicates 0.0045. So if you want to know the exact value, so just click here, tools, you will be having an option query. On the query option, you can see there was probe values. Just click on the probe values. Now, what we are interested in the nodal displacement. So here you can see, we can ask node. Here you need to select nodes. So once you select the nodes, where we are interested in the rightmost node. You can see it is showing 2. That means Abacus also numbered that one is node number 2. And you can see U1, just look at the screen, you can see U1 is equal to 0.0045, which indicates that displacement is 0.0045 on the free end. What do you need next? What do you need next? You need next the reaction force. So reaction force you are going to get here. Reaction force, it stands for RF. RF stands for reaction force. So remember that when you look at here, remember that the reaction force is going to apply here on the fixed end. So wherever you put the displacement constraint, where F1 is going to act. And remember that on the right end, you don't have a reaction force. You have only applied force. So the reaction force on the right end will be equal to 0. And the reaction force on the left end will be equal to minus 10 kilonewton, 10,000 Newton. So come back. So just select reaction force. You can see reaction force magnitude. What we are interested, reaction force along x-axis. Reaction force along x-axis, RF1. 1 stands for x-axis. Now you can see here. On the free end, you can see here. Free end, you can see here. Query and the probe values. Where we are interested in the reaction force. Reaction force, you can see here. Is minus 10,000 Newton. You can see RF1 is minus 10,000 Newton. Remember that the minimum reaction force is equal to 0, or that is going to happen on the right end, and the maximum reaction force is going to act in the left end. And while you can see there is always some variation. On the right end, you can see node number 2 reaction force is 0, and the left end you can see the reaction force is 10,000. If you look at any other section, you can see it is coming in between the two values. We will be discussing about these abnormalities later. So you can see here it is 0 and it is minus 10,000. So which is the highest value? The highest value is 0 and the lowest value is minus 10,000. That is why you can see minus 10,000 is shown as blue color and 0 it is shown as red color. 0 is maximum and minus 10,000 is a minimum in this case. So node number 1, you can see it is node number 1 and you can see the reaction force is minus 10,000. That is what it is going to show it here. This is how you need to solve this problem. You can save the data. So this is the solution of this problem. Thank you.